Okay, this is the review for the test on Unit 5, Work, Power, and Simple Machines. The first section is multiple choice. The base unit of energy is the joule, choice A. The others are measures of force and power, and mass and distance. The base unit of force is the Newton. The acceleration we use to calculate weight. So anytime there's a question about weight, you're usually given mass, which is in kilograms. That's not the same as weight. So we have to use the force of gravity to calculate the weight. Gravity is always 9.8 meters per second squared. So whenever you're talking about the weight of something on Earth, take the number of kilograms multiplied by 9.8. Which of these ways is not a way that a machine can make work easier? Well, a machine cannot change the actual amount of work that needs to be done. It can do a lot of things. It can increase the amount of effort you put in, but it doesn't change the amount of work that gets done to the load. The load is what it is. It's got a certain mass, a certain weight, and it's moving a certain distance. That doesn't change. What changes is how much effort you have to put in. That's what the machine does. It gives you that mechanical advantage. Okay. Power is measured in watts, which is a unit of energy over time. How much work will Brian do if he lifts 6 boxes from the floor to the shelf, and the boxes have a mass, okay, key mass, of 15.4 kilograms. So mass is not weight, so first we have to take the number of boxes, which is 6, and then convert the mass of 15.4 multiplied by that acceleration of 9.8, and that gives us a total of 905.5 newtons of force. That's how much it weighs. And then to find the amount of work, we multiply that by the distance, which is 1.4 meters, and that gives us an answer of 1,267.7 joules. Okay, if we're taking 5.3 minutes to perform 894 joules of work, what is the amount of power? Well, in this case, the distance here isn't really going to be used in the problem because we're already given the work, which is the distance, includes the distance. So 894 joules, that's how much work she did, and that gets divided by the time, which is 5.3 minutes. And then we have to convert the minutes into seconds because the time has to be in seconds, so it would be divided by 318. And when we do that out and we round it, we get 3 watts. It comes out to about 2.8. If we're carrying library books upstairs, okay, so we've got to take into account that there are 12 stairs. It's the 3rd floor, so that means 2 flights of stairs. So 24 stairs total. Each stair is 19.7 centimeters. We're going to multiply the 12 steps times the 2 flights of stairs times the height of each stair. And actually, we're going to put that into meters. So we move the decimal over 2 places. So it's 0.197 meters. Okay, so that's the total distance times the mass. Right? The mass is the number of kilograms times 9.8. And there are 15 books, so we got to multiply all those numbers together. 12 times 2 times 0.197 times 43.5 times 9.8 times 15, and when we do all of that out, we end up with 30,000 joules. Okay, the next multiple choice section. A first-class lever would be none of these examples, actually. You might think it's scissors, but scissors is actually a pair of levers combined, which makes it a compound or complex machine. A third-class lever would be a shovel. Okay, a third-class lever has the fulcrum, the effort, and the load. So the fulcrum and the load are opposite ends. So the fulcrum is where your hand is at the end of the shovel handle. Your effort is in the middle, where you're lifting with that other hand, and then the load is at the end of the shovel. The unit of force, we've already actually covered that, is newtons. Which of these will cause the amount of work accomplished to get smaller? Well, work involves force and distance. So if you change the force and or the distance, so the correct answer here is both A and C. How much work will be done by Megan if she spent 46.82 seconds at a power level of 26.46 watts? Well, the work is done, work divided by time is power, which is the watts. So if we do watts times the length of time, we would get the amount of work that was done. And the amount of work that was done in this case is 1238.9 joules. How much power will Nick need to do 855 joules in 94 seconds? So this time we're dividing the work by the time, and the answer is 9.1 watts. Okay, so 855 divided by the 94 seconds. Okay, how much power will Haley use if she does this many joules of work in 1.2 minutes? We're going to have to convert that to seconds by multiplying it by 60. And if we do that out, 4693 divided by 60 times 1.2, you get 65 watts. Okay, and how much work will be done in 2.17 minutes? Again, we're going to multiply that by 60. And the power level is 98, so we're going to multiply 98 times 2.17 times 60. And when we do that, we get, actually none of these answers would be correct. The correct answer would be 12,793.5. So if that's what you got, you did the problem right. That just wasn't one of the choices. The load in a third class lever is opposite the fulcrum. So that's like the example of the shovel. In a third class lever, your effort is in the middle, fulcrum on one end, load at the other. For a first class lever, the ends are the load and the effort, and the fulcrum is in the middle. Okay, so you've got fulcrum, effort, and load. That's a first class. In the third class, you've got fulcrum, effort, and load. And then in a second class lever, the ends in a second class lever are fulcrum at one end, effort at the other, and load in the middle. So the end positions are the effort and the fulcrum in a second class lever. Okay, which of these is not a simple machine? We actually already did another example with this in it. Scissors are not a simple machine. It's two simple machines combined. Levers, two levers, and actually scissors also include an inclined plane in the form of the blade. If you have a two-pulley system lifting a large block, you actually do the same amount of work that the pulley does, which doesn't sound like it would make sense, but the work gets divided evenly between you and the pulleys, so the work that you have to put in gets cut in half. So you're doing the same amount as the pulleys. Someone using a hammer, well, you're using a hammer. A hammer uses a lever to increase the amount of force. An axe beside a pile of wood. An axe, the main machine part of an axe is the wedge of the blade. You could make an argument that it is also a lever, the same way a hammer is. So I guess you could accept either one of those answers. The last multiple choice question, going down a slide, that would be an example of a ramp, a simple machine. Okay, moving on to a couple of problems. Simple machines, I'm just going to talk through these couple instead of writing them all out for you. Simple machine families are levers and inclined planes. You could include levers, pulleys, wheels, and axles under levers. You could include inclined planes like ramps, wedges under inclined plane, and also screw would be inclined plane. So any of those in combination where you have at least one from each family and a total of 4 would be okay. A simple machine is a machine that uses a mechanical advantage to change the direction, magnitude, or both of the force that's put in. So that's the definition of a simple machine. The wheelbarrow image did not get copied in, but to do a simple version of it, A wheelbarrow has a barrel in the middle, a wheel on one end, handle on the other. So the effort is where the handles are, where you lift. The load is in the center, and the fulcrum is the point. The axle of the wheel is actually the fulcrum for the lifting portion. Okay, and finally, this is got a bunch of stuff going on. Okay, so the amount of power that will be used. So power, we need time. We've got minutes. We're going to need to multiply that by 60. We've got a number of boxes, 13 boxes. Each box has a mass of 32. There are 17 stairs, and we're going to the 4th floor. So 17 stairs times 3, because you have to go up 3 flights of stairs to go from the 1st floor to the 4th floor. And the height is 19.8 centimeters, or 0.198 meters. So that's going to be 17 times 0.198 times 3. That's going to be the distance, which comes out to 0.098 meters. The force is 13 boxes times 32.3 kilograms times 9.8, which is gravity. That comes out to 4,115 newtons, 0.02. When we multiply those together, the force times the distance gives us the work, and that comes out to 41,553. $41,553.47, and then we're going to divide that by the time. 12.8 times 60 is 768 seconds. So 768, when we divide those together, the final answer, the amount of power, is 54.1 watts. So there's your final answer there, 54.1. Okay, so there you go. You need to know your formulas, right? Force equals mass times acceleration. You need to know that work equals force times distance, and that power equals work over time. Make sure your time is in seconds. Make sure your distance is in meters. Make sure your acceleration, if you're talking about weight, is 9.8. You need to know all of those things. You need to know your definitions and diagrams of simple machines. And then you should be in pretty good shape from there on out. So there you go. We'll see you for the test.